So I'm going to speak about a topic that is on the fly for some times now. It's about the slice duration and how to order tasks, how to make some tasks running first without breaking the fairness. So yeah, the fair task ordering is something that have been discussed at LPC and previous OSPM. And the goal is really to run some interactive, what we call interactive tasks first, as long as they don't use more than their memory, their CPU bandwidth. So with the introduction of the EEVDF and the custom slice in EEVDF, we now have a way to order task execution because of task with a shorter slice should run first in theory. So my topic was mainly how to select a CPU for task with a shorter slice. But before that, while doing some status, I have found that even before selecting a CPU, we still have some improvement to do on the basic task selection. So in fact, the tests have shown that we have some outlier value, even in some, I would say, default or basic configuration and use case. So I will start with the status of the current scheduling latency for short running task with how to fix this outlier value. And then I will finally go back to the slice in the CPU selection and how that can help for some final out of let's say, an unfixable, easily unfixable situation. So the scheduling latency. So in order to test the scheduling latency, so I'm using cyclic test with different other benchmark, which is overloading the system. In my case, so the goal is to set a short slice of 8 milliseconds to cyclic test and to set 20 milliseconds for all the other one. The main reason is that right now the default value is 2.8 milliseconds, which is already quite short. And in order to run first, that means that you should probably ask for an even shorter slice duration, 1 millisecond, less than 1 millisecond. But we don't have that much task that want to run less than 1 millisecond. So the goal there is mainly to say, okay, if we increase the default slice duration of task, then we can easily make some tasks running first, even if they want to run 4 milliseconds, 5 milliseconds, without breaking the fairness. So that's why all the tests that I have done is basically 8 milliseconds for cyclic test and 20 milliseconds for everything else. So cyclic test when it's idle, the results are pretty good, I would say, of course. That just give us the basic things. So I have removed the average, the median, and all of the things because they remain pretty okay. It's really about the extreme value. So when I run cyclic tests with one always running task per CPU, the results are also pretty good. The maximum start to be large, 9 milliseconds. It's around the 8 millisecond slice. So we'll come back on that later on. But yeah, you can see that at some point we haven't been able to be scheduled before other tasks, and we have to wait for the full slice. But yeah, those results are not always good, especially when you start to overload your system. And when you use Hackbench is really stressful in terms of number of wake up, sleep, migration, some short idle time. And in this case, we see that not only the maximum value is large, but only the 99.9 percentile, which is above 4 milliseconds. So it means that we have a number of wake up for cyclic tests where you have to wait 4 milliseconds, which is a bit too much. And then if I use cgroup, that was the other things, that's even worse. Even the 99 percentile start to be large compared to a cyclic test that mainly wake up and sleep. So in all the tests, we don't have any problem about using more than our slice because cyclic test is pretty much doing nothing. So, yeah. So the main result is that this short slice task doesn't always preempt current. Cyclic test, we can't say that because he used more than his CPU share because of the way it's working, which means that we have some other problem. And the hack bench, as I mentioned, yes, it's stress the wake up, the NQ, the DQ, and it just stress all the corner case with the EEVDF. So the first one, which have been queued for 7.1, I think, it's the negative lag. So it was, yeah. So I just spent some time looking at tracking with ftrace and something. Yeah, that's another thing. I have used ftrace synthetic workload just to stop the trace when the scheduling latency was above a value. So for example, in this case, above 5 milliseconds, it was pretty easy to catch exactly when you have this outlier. And with some additional trace in the scheduler, you can easily understand why you are not preempting the running task. So the negative lag for delayed DQ is the first one. So in fact, before I saw that, it was something I never thought about, but yes. When you stay enqueued because you want to decrease your negative lag, it can happen that some new task enqueued with some positive lag, so it will move backward even more the average runtime, so it will increase your negative lag, which means that the task that stay enqueued in order to remove its negative lag will at the end get even more negative lag, so it will be delayed even more before being scheduled. So it's pretty easy. The test was pretty easy to just when you're about to enqueue the task, make sure that the negative lag is at least the one that you get when you went back to sleep. So that helped to remove a number of large scheduling latency value. That's the first thing. So we can see that now the 99.9 is above 1 millisecond, which start to be better. The maximum value is a bit better, but I would say that the maximum value is moving quite a lot. So from one run to another one, maybe I can get a 9 milliseconds. So that was the first one. So that was so in this case, it was mainly everything in the root group. Then the next buddy. So when I was running with C group, I was seeing some this large value as well. And what's happened is that when you look if the waking task can preempt the running task or not, we have this peak buddy bypass or shortcut where you try to favor the buddy that has been set. And in our case, it's happened quite often that yes, the buddy was set. So we were bypassing all the EEVDF peak. And we're just saying, okay, we can't preempt or we will not preempt. So in this situation, the goal was to clear so at least to check in EEVDF that if we don't take care of the buddy, will be picked as the next task to run. And if it's the case, then you clear the buddy. So this made some large improvement in the C group case. So we are back at the 99.9 percentile. We are back below the 1 millisecond. So that was one thing. The next one, the delayed DQ entity. So then there are also some situations. So when a task wake up with a short slice or a shorter slice than the running one, we look if we will be picked. And in this case, we just set the need reschedule and the goal is to be picked. When we go in the picked EEVDF case, so we have some delayed DQ task. By default, delayed DQ tasks have deadline that has been set for a while. So the deadline of this delayed DQ are often quite close to the average value, which means that a short task that will be placed can often have some a deadline which is after the delayed DQ. But the main problem is that the delayed DQ will never, we will only DQ that. I mean, if it's the next one to be picked, we'll just DQ and that's it. But because it's there, we are not preempting the current task. So in this case, what I have done is that when we are checking if we could preempt, so when we are picking what will be the next in the wake up preempt, if it's a delay DQ, I DQ that and I recheck what will be the next one.
Yeah, so I think I want a small change to the patch, but we'll put this in 7.1 as well.
Yeah, so initially I was looking if I could skip the EEVDF in the peak, the delay DQ in the peak, but then we lost all the
just
RB3,
DQing it is right.
Okay. So with that, we've got an additional benefit. So we are almost half a millisecond. We still have some large value for the maximum. So with all these 3 patch, I have been able to reach the situation where from the 99.9 above several milliseconds, below almost half a millisecond. Except for one use case I still need to understand, and that's probably coming from the other pending problem. So we have a bit of a picture now with Hackbench, with RTApp, with or without C group. Surprisingly, Hackbench will trigger some corner case, but using RTApp with some tasks that wake up and sleep regularly, if you have more than one, trigger also some other interesting use case and corner case. So we start to be an interesting value to be used in the task placement or in the selection of the next running task. There is another one. So first of all, do you have any questions for the yes?
Sorry, I'm not sure if I misunderstood, but how do you measure the scheduling latency? Is it just for the test process, or is it for the whole system?
For the cyclic test only.
Just for the cyclic test.
Yes.
And you measure it on every task scheduling. On every
yes, I'm using the ftrace. I'm using, in fact, I have reused what have been written. I don't know if it's you, Stephen, who wrote that in the documentation. So you can create something. You can track the waking of an event of a task and the switch of a task, and you can
synthetic events.
Yes.
Okay. So the percentage is over the number of wake ups, basically.
Yes.
Okay.
I missed this, but what's the utilization that you're running all this at?
Sorry.
What utilization are you running the test at?
The utilization.
Yeah, like the CPU. How busy is the CPU?
So. The system is fully, the utilization, we are the max, all the CPU are fully busy in this case.
Oh.
Almost. With the Hackbench, yes, we are 100% use. And for RTApp, maybe a bit less, but usually it's quite close to the full-time utilization. Yes? It's the full. Yeah, because with the lazy, that would be even worse, because at the end, in the wake up preempt, we are setting a lazy one. So,
yeah. So just a question of this is something that we did that would never be pushed upstream, because I know Peter would knack it right away. We actually found great performance when we just disabled eligibility altogether.
Yeah.
But what my question would be curious is run these tests. If you were to disable eligibility, just obviously it's not the solution because it removes all fairness. But if you were to delete it, just to see how that compares. Like ideally, we want to perform as well with like eligibility disabled for cyclic test. But I think that's kind of the goal to get to. Of course, that's not the solution because there's obviously issues with doing that.
So I haven't tested it without with disabling eligibility. What I did, and I mentioned that a bit later, I have disabled the run to parity feature. Okay. And I will show that later, but the maximum is better because every 700 microseconds you can switch to another one. So the lag remains really close. And even if you fail to run first, after less than a millisecond, there is a chance that you will run anyway. Yeah. So the maximum value decreased quite a lot, but from 99.9 or even others, we are pretty close, in fact, with all the patch.
Okay. But isn't eligibility already disabled for wake up somehow?
I don't think so. The DQ is the delay DQ was the thing. Someone sent a patch before, and when we did that, we got almost the same with the just ignoring eligibility on wake up. We actually got almost the same performance, but just disabling it. So the wake up is the issue.
Yeah, but that bench is really wake up intensive. So I was thinking
exactly
if that's
that was
we don't have to disable eligibility in general, just
Right.
wake up maybe.
But no, but I think
But
that's
it's
still, that you can still play games to, cause unfairness by doing that.
So another one, which are in fact when we check it for if we're able to preempt the current running task, and by the time you will be picked as the next running time. So this sequence is not atomic. So you can run in the wake up, decide, say, okay, I'm the next one to be run. It's fine. So I set the risk head, and then you release the lock and you start to pick the next. And in the meantime, some other tasks can have been enqueued with some positive lag, which means that the average runtime will go backward. And by the time you go to pick the next task, your task is no more eligible. So we are in this situation where, I mean, yes, in 1 microsecond or even less, you from eligible, you become not eligible anymore. So I have tried to play with the next buddy to force the entity. Say, okay, if I have been the one that have set the need risk head, why not setting me as the next buddy because I'm the one that I should run? The first result that I have are not really conclusive. So for now, I haven't pushed. Maybe I'm doing something wrong.
But even next body, we check eligibility.
No.
We don't.
Oh yes, you're right. No, yeah, you're right. Yeah, you're right. But yeah, the next buddy in this case, but in this case, I can skip the eligibility because I was eligible at the time. But yeah, by default right now, yes, we look for the eligibility. So this situation is still there. I don't have any simple solution so far, but I will try to find some. We have another thing is the positive lag. So our positive lag, once you are dequeued with a positive lag, the lag will be there forever. I mean, at least until your next enqueue. So if you're a task that wake up I wrote an hours, but 100 of milliseconds, you can have you can preempt everybody because of a lag that is probably no more relevant 100, 200, 300, 400 milliseconds later. So for the negative lag, we have this delay dequeue that help to say, okay, you use more than what you should have done, what you should have used, but now you wait enough that we can remove your negative lag. So the goal would be, should we do something similar for the positive lag? I mean, when we enqueue and we see that the sleep duration, based on the sleep duration, to say, okay, we should decrease the positive lag because it's meaningless now. That's something I would like to look at. I haven't run. And even more.
What problem does that cause? Is just the fact that this guy now has, for a while, it just happens to always preempt everything?
Yeah, and with the run to parity, in fact, because you let, for example, you have 2 tasks. In my case, you have 2 tasks with 20 millisecond slice. So when we run first for 20 milliseconds, the other one will increase his positive lag because he's waiting. Mm-hmm. If at the end he runs for only a few milliseconds and go back to sleep, then you will get a positive lag of 9 milliseconds, which means that the next time that you will go back, you will have a positive lag of 9 milliseconds. So his V-run time and his deadline will be moved backward, and probably the deadline will be before a short time task.
So one of the ideas that I have in my crazy basket on the to-do list is track a generation number for every time that the run queue loses contention.
Okay.
Basically, when you go idle.
Yeah.
And then only preserve lag as long as the generation is the same. Because I mean, if you lose contention,
yeah,
all service distribution goes out the window.
Yeah, that could be
sort of.
Yeah.
So if the system goes idle, basically zero everyone's lag. Positive and negative.
That means that the task will then be scheduled on the same CPU, otherwise.
Yeah, so migration will need to be, you need to migrate the generation number along and then yada, yada, yada. But it's on the crazy ideas to play with list. And I
that might be interesting.
Time.
Yeah. Yeah, that could be a way.
It might be terrible, I don't know.
So we have this so far. And then, so our EEVDF, it's earliest deadline first. So whatever your slice duration, the task with the earliest deadline will run first, even if it has a longer slice. And so, I mean, this will always happen. We can't remove all the case where the longer slice will run first. The only thing is that when you are setting a slice right now, you're also setting the max running duration of a task before looking for another one. So that that's not, so setting a slice, that's probably something everybody needs to be aware of. Setting a slice duration, it's not setting a scheduling latency. It will impact your scheduling latency because you will shorten the running time of everybody. So if you are the third one, you will have to wait a shorter slice than others, but you can still be the third one to run.
And many of the interactive things are short running.
Yeah. And also, yes, so the run to parity, to go back, is favoring this situation, but by delaying the switch. So it's happened more often with run to parity than without. But we also want to keep run to parity for other good things. The EES is also favoring this too, because it's packing tasks. So the task will have to wait, so you can have more and more tasks. So yeah, this for that I need all this needs further investigation. How we can go over this situation. So yeah, I have mentioned quite a lot the run to parity. So the run to parity help us to ensure some longer running slice and minimize the context switch overhead. So for throughput, it's better, but it increases the scheduling latency. So when you disable the run to parity, the slice is less than a millisecond. And in all the tests that I have run, so the maximum latency is better. So we are around 2 or 3 milliseconds at max, which look, because the context switch is happening every millisecond, or I'm using a 1 millisecond tick, by the way, for performance. But for the 99.9 or the 90 percentile, the results are pretty similar with or without. So that's really this last use case where you fail to preempt the running task. And yes, in our case with cyclic tests, 7 microseconds is quite enough. I mean, it's even too much. But in a real use case, we expect the task to run probably more than 700 microseconds. 1 millisecond doesn't seem to be a silly duration. So in this case, you will run first, but you will not be able to do all you want, and you will be preempted, and you will have to wait for others to run. So at the end, your full-time execution will not be better. So is there any question? So yeah, in any case, it can happen that you will not be the next one to run. We can't fix this situation just because, yes, the task with the long slide will run first, or there is another task. So in all the tests that I have done so far, I have only one cyclic test running, so it's the only one. But for sure, in a real use case, you will have several short slice tasks that will wake up, and most probably simultaneously, especially if you look at the display pipeline, something like that. Or just because, yes, you have a task with a higher priority, that's right. I mean, a RT task, deadline task, whatever. So we have to handle the case where you will not run first. And that's where I'm coming now. So in this case, in order to minimize even more the situation, the goal is when we are selecting a CPU, right now we are only looking at idle CPU or less loaded CPU. The goal would be to select a task where we hope to run first, and typically a task where a CPU where the mean slice duration is bigger than our slice duration. But for that, we need to access the mean slice of the CFSRQ, or at least the target and the root. And during the select CPU, the RQ is not locked, so we need lockless data. That's one of the first problems in this case.
Well, that's easily fixable, I think.
Yeah. So yeah, we need to maintain a lockless value of per CPU mean slice in a lockless way, and the goal would be just to save when we are getting the CFSRQ mean slice to save the value in a per CPU. That might even be reusable, and we could prevent the call to this, even if the CFSRQ mean slice function is not that huge. I mean, if we can save some comparison.
Yeah, it's a bunch of pointless dereferences.
Yes. So once we have that, then we can do a first pre-selection in the wake caffeine, typically. So idle CPU always better because we will run first. We will probably have some exit idle latency problem, but that will be another problem. And before, so in wake caffeine, we are looking at idle and then wake. So the goal would be to add an intermediate step where we are looking at least between the two CPU if there is one that is better than the other one. And in this case, we'll select that. In ES, that's a bit more tricky because right now we are only looking at the energy. So there is we need to rework that so that we can, between two CPU with similar power consumption or energy impact, select the one with where your slice will be shorter than the running one. And in the select idle sibling, all this fast pass, then the goal would be to track this CPU when we are looking at all the CPU. And among those which are not idle, select the one, keep the one with the highest mean slice duration, so you can preempt that.
When you say looking for a non-idle CPU and select idle sibling,
yeah.
Where are you exactly? Like one of the early exit criteria, or when we really search for an idle CPU?
So at least in the for loop, but probably, I mean, if we are not idle, we can easily add this one as a potential in the early test. We can, if we are not idle, we can probably look at that as well. That's a cheap comparison, I would say.
For all of us, for the interactive ones.
So the goal will be just to compare your slice. So either I can take the custom flag as a trigger, but otherwise it's mainly about comparing the slice of the waking CPU of the waking task with the per CPU slice. I don't know. I probably need to see the overhead, but.
So if long slice means sort of like shit bash or whatever, and
No,
and I'm interactive, I'd want to be on that CPU, right? Because
a long slice, it's not correlated to batch. I mean, we can be nice idle, scale idle, or batch, but then
no, it's not really,
yeah.
but like some like it expresses similar thing.
Yeah.
So I wouldn't want all the short slices necessarily on the same CPU, but rather.
Sorry, I'm not sure.
Well, so he's trying to spread them. So basically, wake to the CPU that has the longest slice.
Ah, yeah, okay.
So the probability that you will run first will be increased.
Right.
It's not a 100% win, but at least. Yeah.
Well, if you do this in wake caffeine already, right? If you choose this or pref CPU, then you still have the second step. Then.
Yeah.
Okay, but what does the initial CPU has to do with when you look for an idle CPU, for instance, and you figure out like I take another one, then you know what I mean?
Yeah, I understand, but it's just that the target CPU is where you start. So the goal would be in this case, you will look for your target CPU first as the one that you can use. Now, what I haven't done yet, so I haven't really tried that. I don't have any number to show. And the main things is that you want to stay on the target CPU in priority, I would say. So that's why that's a way to make it the first one to be selected.
Yeah, I would understand if like sys util would tell you there's no way you don't have to look for an idle CPU.
Yeah.
Then in each of those exit criteria where we say we have to use a CPU, then you can make a decision. But when you go through the list of MC domain CPUs to find an idle one, but yeah, we will figure this out.
Yeah.
Have you looked at the code in CPU Pry?
What CPU?
CPU Pry, it's a priority of CPUs. It's for this case, how RT finds how to migrate to the lowest, or the CPU with the lowest task or priority task running on it. So it's kind of a matrix of CPU masks of priority levels. And it would just say, okay, and it starts off, okay, like there's a bit mask of all the priorities with where things are set, and I'll find the lowest priority first, and then say, okay, here's the bit mask of CPUs that have the lowest priority, and then it would check to see the affinity of the task. See, can it go to any of these? If so, pick one, or take that mask and pick one. I mean,
Scalability of that thing is a nightmare, though.
What?
Scalability of that thing is a nightmare.
Yeah, people are already complaining when we loop on all the CPU looking for an idle.
Well, no, we don't loop on all the CPUs. No, it's not scalability of CPUs. It's actually scalability of priorities. So and it's also, it has a bit mask of priorities. So it only loops for the number of different priorities.
It makes the lookup cheap.
Yeah.
It makes the update expensive because your cache line.
Yeah, you have the cache line because you have cache line contention.
You need to update on every NQ and DQ, which is a nightmare.
Only if the I guess the like on changes of the slice, the expensiveness of it, is that changed on every NQ, DQ, or?
Well, yeah, because we're looking at the min slice, and if the task set changes, this min slice can change. This can be very, very frequent.
Yeah, even more if we start to have some short and long. I mean, that will not be a binary value at some point. You can have, I would say, from.
So deadline has a
100 microseconds to 100 milliseconds.
For a minimum deadline.
That's something you look at.
Yeah. I agree.
Vincent?
Yes.
I'm more interested in this EIS change that you are proposing, how that would fly. Are you going to loop over all CPUs in the domain, or? No,
I was planning to do something similar to what I have proposed previously, where so yes, probably at the end, in some case, yes.
But you also need you have similar issue that you also need to update that every DQ by MQ.
Yeah.
Did you track that per CPU?
Yes, the goal is to have a per CPU min slice. And we already, I mean, when we NQ or DQ a task, an entity, we already tracking that. So just instead of computing that for each and every case, just save this value.
Yeah. One question.
Yeah.
Like if you have C groups involved with this,
yeah.
It will select what?
So the min slice is propagating all around, but I need to check, because even if it's propagated, that I mean your group entity might not be eligible by the time. So that's another level of complexity. Yeah.
Vincent, the highest min slice is relevant within the same LLC.
Yes.
So you don't bound.
No, but by default, all the wake up we are doing, it's in the same.
Yeah. The same
stuff.
Other questions? Yeah. And yes, and the goal is that based on that, so it's at the select run queue at wake up, and we also have this will to have the push callback mechanism, which means that even if you select a CPU and you end up not being the first one to run, the goal will be to put you in the push callback list so that you can be migrated on another CPU and you will not have to wait for the 1, 2, 3, 4 milliseconds, 10 milliseconds before being scheduled. But because the goal is that the push callback use the same function as the wake up, the select task, and the function will be the same. It's just that we can call that even if you are already runnable. And that's it for me.
Yeah.
How many time do we?
We have at least 10 minutes.
10 minutes. So if you have any question or comment or suggestion.
Well, just trying to think through if you can select out a sibling.
Yeah.
And it would be sort of, it's tempting to compare idle exit latency with slice duration. I think that's a red herring. But...
Yeah, it's just also when we are, I mean, all this is a lot less when we are looking for the energy efficient CPU. We already have the problem. And that's why the push mechanism is a way to overcome the case where finally, by the time you select a CPU and the time you enqueued, anyway, someone else can have enqueued in between and preempt you. So we will never be able to select the right CPU 100% of the time. So instead of trying to do that, in this case, we have this fallback to say, okay, we select the wrong one.
So this is why we do the for each CPU rep,
yeah.
So that you have a higher probability of not all selecting the same CPU.
Yes. Yeah. Yeah, but even with that, I have seen this situation where in between, I mean, I think in some cases it was five Hackbench tasks which were enqueued between the wake up preemption test and the enqueue.
But if you have all CPUs start looking for an idle CPU from CPU 0 onwards,
yeah, no, I agree.
Guaranteed to all pick the same one.
Yes, I agree on that.
Is there some other way to extend using the bin slice to figure out how long you would wait on that CPU? So if the point is to say, I want to reduce my scheduling latency as much as I can, is there some way to?
So yeah, there is few other things right now. Also in there are, so I haven't yet figured out all the root reason of this large maximum scheduling latency. And it also might be that in some case, we keep protecting the running task a bit too much because we are using this new slice, min slice, but in some case, we can see that this will delay.
So the paper doesn't do preemption, and it just says if we pick the slice, we run it, and then the maximum latency is basically the max slice in your set. And I don't think that is an unreasonable constraint to have. If you run 100 millisecond tasks, and at some point you need to wait 100 milliseconds to get on.
No, yeah, the point there is mainly, I have seen in some case that, so you have two tasks with this 20 millisecond slice duration, and so the short task wake up, we will update the protection to only 8 milliseconds, which is already larger than the current protection. So it's an up. And in fact, it just, you also have at the same time another task with this long positive lag. And we should probably in this case just remove the protection because it's already too long. That's my point.
Yes.
That I think there are some cases, but the goal is also to keep having long slice duration most of the time. I mean.
Yeah, because like you said, if you do remove the run to parity or remove all the protections, you'll schedule yourself to death. It's endlessly small.
I agree.
And I mean, we always have sched deadline. If you actually know what your periodic workload does.
Yeah, no, at some point I agree. If you want 100%, running fast, schedule deadline is probably your solution. I agree. Thank you.
Okay, thank you.